In this work, we introduce importance of self-consistency in active learning for semantic segmentation. State-of-the-art supervised semantic segmentation models need a tremendous amount of labeled data to learn a large number of parameters. In semantic segmentation that every pixel is associated with the label, collecting dense labels is costly and time-consuming. Active learning proposes a compelling solution by iteratively selecting the most informative samples to label. It can significantly reduce the cost of human labeling by detecting and annotating the regions that reduce the uncertainty of the model the most. In this work, we improve the uncertainty measurement during the active learning process by using the horizontal flip inversion of the input image in addition to use the input image. Lack of generalization is another well-known problem in deep learning models. Even with having a large number of data, deep learning models can still suffer from poor generalization. Different approaches such as dropout, ensampling, and augmentation propose to increase the generalization in CNNs. In this example, we show that despite using data augmentation during the training, the segmentation model still suffers from poor generalization for a simple transformation and fails to have a robust prediction when the input image is flipped. Given the input image and the model prediction, we expect to have similar predictions if we simply flip the input. However, we observe that the model prediction changes as we flip the input. This kind of inconsistency and high variance affect the active learning process directly and cause the model to select the wrong sample as the most informative sample during the active learning process. To improve the generalization of the model, we utilize the rich self-supervisory information and reduce the uncertainty of the network by enforcing a pixel-wise self-consistency between the output of the segmentation network for each image and its transformation. Given an unlabeled and labeled dataset, our goal is to achieve the highest performance possible by iteratively adding new labeled data until we reach a certain budget. At each iteration, our goal is to find the most informative unlabeled image patch to be labeled and be added to the labeled dataset. The active learning process is repeated till the labeling budget is exhausted or until a certain model performance is reached. Our active learning process consists of two steps for each iteration: label acquisition and updating the semantic segmentation model. Let's walk through our algorithm. For each iteration, we go through all the images in the unlabeled dataset to select and label the most uncertain region. For each unlabeled image, we use both image and its horizontal flipping to measure its uncertainty. We send each image to the semantic segmentation network and measure the pixel-wise entropy by aggregating the posterior uncertainties over the network predictions. We then look at the regions among all the unlabeled data that has the highest entropy. After finding the most uncertain region among all the unlabeled data, we ask an oracle to provide the label for the selected region. Images which contain labeled region will be then added to the labeled dataset. If an image is fully labeled, it will be removed from the unlabeled dataset. After updating the labeled dataset, we update the model with the labeled region. In this stage, in addition to the cross-entropy loss, we enforce the predictions for the input sample and its transformation to be consistent. After meeting the budget, the active selection process concludes with the retraining of the network with the final version of the labeled dataset. We refer to this stage as retraining stage. We evaluated our method on two semantic segmentation datasets. We first compute the upper bound performance of the semantic segmentation model for each dataset denoted with the solid line. We see that for low budget size, entropy and random baselines suffer from cold start problem. In contrast, our method achieves significantly better performance in the low regime data. Using our proposed method, we achieve 96% of the maximum model performance with labeling only 12% of the data. Furthermore, we show that by using the self-consistency loss in addition to the cross-entropy loss, we achieve better performance for both active learning and fully supervised models. Here we show the qualitative comparison between our model and the entropy baseline for the budget of 12%. We can see that the entropy baseline fails to segment sidewalk and train comparing to our proposed model. Moreover, we show that we can even improve our result further by adding the proposed pixel-wise self-consistency loss.